The subject this week is magnetic fields and forces. In other words, an overview of magnetism. So it's chapter 18. There are 6 sections in the chapter. And part 1 of the screencast will be on the first 3 sections. Really, it's on the magnetic force. So let's start with an introduction. I suppose everyone has played with iron magnets and observed their surprising forces. If you have 2 bar magnets and you orient them south pole to south pole, there is a repulsive force. There's a repulsion. Or north pole to north pole. But if they're oriented south pole to north pole, then there's an attraction. So why do these forces occur? Well, we can describe the forces in terms of poles and dipoles. Poles refer to the north and south pole of a magnet. But magnetic poles never exist in isolation. Any magnet, any piece of magnetized material, will have both north poles and south poles. And it's not possible to separate one pole. So magnetic poles never exist in isolation. But if they did, then they would experience repulsive and attractive interactions similar to electrically charged particles. If you could create an isolated north pole or 2 isolated north poles, they would repel each other. There'd be a repulsion, or 2 south poles. But if you could isolate a north pole and a south pole, they would attract each other. So it reminds you of 2 charges, positive positive, or negative negative, electric charges. Like charges repel, or a positive and a negative. Unlike charges attract. Well, this isn't what causes magnetism, or the magnetic force, because magnetic poles never exist in isolation. Magnetic poles only exist in equal but opposite combinations. And a good example of that is just a bar magnet, like you probably had as a child, as a toy. A bar magnet is a magnetized piece of iron. It has 2 ends. One end is the north pole, the other end is the south pole. And if you tried to separate the north pole from the south pole, suppose you tried to cut the magnet in half, you would not have an isolated north pole and an isolated south pole. When you cut it in half, the left half would be a north pole and a south pole. And the right half would be a north pole and a south pole. Now, if you have 2 bar magnets, and they're oriented in this way, with the south poles closer together than the north poles, then that will have a repulsive force, because the force between the south poles is stronger than the force between the north poles. The south poles are closer together. So that gives a repulsion for this orientation. On the other hand, if you had the other orientation, then the north pole would attract the south pole, And that would be a stronger force than, for example, the repulsion between the South Pole and the South Pole, or the North Pole and the North Pole. In this orientation, there's an attraction, an attractive force, because the closer together poles are south and north. All right, so we haven't explained why these forces occur. These are the forces that you observed when you were a child playing with toy magnets. But we haven't explained why they occur. We've said that, well, if there were magnetic poles, then that would explain it. But that doesn't explain it, because there are no isolated poles. Poles never exist in isolation. So we still have the question, why do these forces occur? Why does a magnetized piece of iron have one end, which is a South Pole, and one end, which is a North Pole? Well, now we come to magnetic dipoles. Oh, let's look at this picture. A bar magnet is really a dipole. It has two ends. One end is the North Pole, one end is the South Pole. So it's got two poles. Always it has two poles. So it's a dipole. Now that dipole characteristic of magnetized iron, it goes all the way down to the atoms. Each atom is a tiny magnetic dipole. So let's just think of a single atom and the magnetic field around that atom. Well, there's a North Pole side and a South Pole side. The magnetic field comes out of the North Pole, goes around, and comes into the South Pole. Just like if you had a positive charge and a negative charge, the electric field would come out of the positive charge and go into the negative charge. Well, the magnetic field is the same way with North Poles and South Poles. The magnetic field comes out of a North Pole and goes into a South Pole. And there's a kind of visualization of the magnetic field. Now, we've seen these field lines in the case of the electric field earlier. Actually, this picture goes back to the great Michael Faraday. Michael Faraday, the idea that magnetism has a force field was first expressed by Michael Faraday. When he called the force field B, he called that the lines of force. And this idea, his idea, was based on his famous demonstration of iron filings sprinkled on a glass plate above a bar magnet. Here's a picture of that. Take a bar magnet, rest on top of the bar magnet a thin glass plate, sprinkle iron filings, little slivers of iron, over that plate, and they will trace out the lines of force. Why? Well, it's because there's a magnetic field created by this bar magnet, which magnetizes each little splinter of iron. Each little iron filing gets magnetized, and then it acts like a compass needle. It lines itself up with the magnetic field at that point. So the magnetic field at that point, on the one hand, magnetizes the little splinter of iron, and on the other hand, exerts a torque on it so that it will line up with the magnetic field. So that was a demonstration that he had developed, and he said, "Look, there's something outside that bar magnet. It's up above the glass plate. There's something there. It's the lines of force. You can't see it with your eyes, but you can observe it if you sprinkle iron filings over the magnet in the magnetic field. Now, we no longer call this the lines of force. Later, James Clerk Maxwell, who was a little younger than Faraday but lived at least part of their lives overlapped, Maxwell created the theory. Faraday was the great experimenter, but Maxwell developed the theory, and he gave another name to Faraday's lines of force. He called it the magnetic field. The notation we use for the magnetic field is always B. It's a function of position. It spreads out over a large volume of space. Well, in principle, over all space. In practice, it spreads out over the space around the magnet that's creating the magnetic field. That's B of x. All right, now let's go back to the question. Why does a bar magnet have two poles? Okay, why does a bar magnet have two poles? Well, what is a bar magnet? Well, it's a piece of iron. There are other materials that can be magnetized, but iron is the most commonly encountered. You have a bar magnet that you played with as a toy when you were a child was certainly made of iron. There are three elements that can be magnetized: iron, cobalt, and nickel. They all appear in the same place or right next to each other in the periodic table. Those are the only three elements that can be magnetized. There are also certain alloys that can be magnetized. Usually they incorporate some iron, nickel, or cobalt. But let's just think of a bar of magnetized iron. Why does it have a north pole and a south pole? Well, remember, every iron atom is a little magnet. It's a little dipole. And if the atomic dipoles, magnetic dipoles I'm talking about, not electric dipoles, but if the atomic magnetic dipoles are all aligned, then you see what you end up with. You end up with this end being a north pole. The north poles here are red, the south poles are blue. So you see how this side of the piece of iron is red. I mean, the colors are just for the purpose of illustration. They're not physical colors. And this side must be blue. So it's overall a south pole. Now, what about in between? Well, there's also magnetism inside the iron, but we're talking about the magnetism outside of the iron, which is mainly depending on what happens on the surfaces. You know, these two dipoles sort of cancel each other out if you're way out here. If you're looking at a point way out here, these two dipoles will cancel each other out because you're very far away. But all of these dipoles will contribute to a magnetic field in that direction. And similarly over here, all of these dipoles will contribute to a magnetic field in that direction. So if we say the north pole, the magnetic field comes out of the north pole and goes into the south pole. So this side will be the north pole, this side will be the south pole. The magnetic field of a large number of sources is just the superposition of the magnetic fields of the sources. So for example, if you had two bar magnets, one would have a magnetic field like this, the other would also have a magnetic field like this. When you add them together, you get the combined magnetic field. Well, in the same way, if you have Avogadro's number of atomic dipoles, magnetic dipoles, the total magnetic field will just be the sum of all those magnetic fields. So for each little dipole here, you'll have a part pointing this way and a part pointing this way. All right, so combining all these atomic dipoles, and the important point is they're all aligned like this. They're all lined up. They're all pointing south goes to north toward the east. The superposition of all those magnetic fields is the magnetic field of the bar magnet, and it will have field pointing away from the right-hand side and field pointing into the left-hand side. And that makes it a dipole with the north pole to the right and the south pole to the left. Next topic. All right, so we've described Faraday's lines of force, renamed the magnetic field by Maxwell, denoted B of X. And we've explained how it comes from atomic dipoles, if you're concerned with the magnetic field from a bar magnet. Later on, in part 2 of the screencast, we'll find a more fundamental reason for the existence of a magnetic field. It doesn't require iron. You can make a magnetic field using copper wire. There has to be current, electric current, in the copper wire. So the fundamental cause of a magnetic field is electric current. And those atomic dipoles of the iron atoms, those are due to atomic currents, electron currents within the individual atoms. So magnetism is ultimately caused by electric currents. You might think, what causes magnetism? Well, a magnet, a piece of magnetized iron. Well, that does cause magnetism, but that's not the only cause, and that's not the most fundamental cause. The most fundamental cause is electric currents. Now, this works in two ways. Electric currents create magnetic fields, and that will be in part 2 of the screencast. That's in a later section of chapter 18. But the other way magnetism and electric current are related is that when a charged particle moves in a magnetic field, it experiences a force. The formula for the force is QV cross B at X. X is the position of the particle. V is the velocity of the particle. The charged particle moves in the magnetic field, and it experiences a force. The charge of the particle times V cross B, velocity cross field. That gives you the magnetic force acting on that electric charge. This formula is called the Lorentz force, after Hendrik Lorentz. Now, this is a single charged particle. What's more common in experience is a current. Consider a wire with current I in a magnetic field. You know, current is just moving charge. So this is the force on a single moving charge. But suppose you have many moving charges making a current in a wire. We saw in the last week how electric current comes from the motion of charge. Well, that whole wire will experience a net force. Each particle, each moving particle, the charges that make up the current, experiences a force, QV cross B. Well, that's altogether the current I times the length of a little section of the wire cross B. So here's the wire. Here's a little section of the wire, delta L, let's call it, is a little section of the wire. It has a direction parallel to the wire, so it's a vector. So there's delta L. And inside that little section of wire, there are many moving charges. A piece of metal wire, there are many moving electrons. They're actually moving in the opposite direction from the current because electrons are negatively charged. But I can think of many little charges moving in the wire. That's the current I, which we studied last week. Now suppose there's a magnetic field present. I don't know, let's suppose there's a magnetic field pointing away from you, pointing into the page. So let's make this the magnetic field. Then there'll be a force on every one of those charges. There'll be a force on this little section of wire. It'll be dl cross B. That'll be the force on this little piece of wire. Now, to get the complete force, you have to sum up all of the little individual pieces of wire. So this symbol S means sum. It's actually a symbol from calculus. In calculus, that's called the integral. But we can just think of it as the sum. We're summing up the forces on these little segments. Now, let's just check the units. This is Coulomb meters per second. This is Coulomb per second times meters. So this has the same unit. Coulomb meters per second. This is also Coulomb meters per second. It's Coulomb per second times meters. So that's why this Lorentz force is equivalent to this force on a wire. Now what's the direction of the force? Let me put the direction in another color. You have to use the right-hand rule. dl cross B. dl is this way. B is pointing away. If the fingers of your right hand curl from the direction of dl to the direction of B, your thumb points in the direction of the force, the cross product. So this is the direction of the force. That's the little force on that little piece of wire. It's perpendicular to the wire. It's also perpendicular to the magnetic field. I'll say more about cross products in a minute. All right, so that's the force on a wire. Now suppose instead of a long straight wire, you had a loop of wire with a current I. So suppose we had, let's go back to green. Suppose we had, try to visualize this in 3 dimensions. Suppose we had a loop of wire and there was a current in this direction. What's that? That's, I guess, counterclockwise. But this is coming out and this is going in. And again, there's a magnetic field pointing away from you. Well, on this side, it's just like this picture. The force will be this way. Now on this side, on the back side, the current is this way because it's a loop. So it's, what's that, counterclockwise. So it's going to the right over here, to the left over here. Well, if I change the direction of DL, I change the direction of the cross product. So on this side, on the far side, the direction of the force is downward. So there's a downward force over here and an upward force over here. The net force is 0. So a loop of wire does not experience a force, does not experience a net force, because there's really forces in different directions. However, it does experience a torque. It experiences a torque about this axis. And so, if the wire is put in this magnetic field, it will accelerate, it will have an angular acceleration. Torque produces angular acceleration. And that's why a magnetic dipole, or like a little atomic magnetic dipole, accelerates to line up with the magnetic field. So we'll come back to magnetic dipoles later. All right, so we've been talking about the magnetic field. We've been saying it's a force field. We can define it in terms of the Lorentz force. The field extends throughout a volume of space, just like an electric field. A magnetic field extends throughout a volume of space. So it's a function of position. The vector x is the position in a point in space. If a test charge is placed at x and is moving with velocity v, then it'll experience a force qv cross b at the point x. We could measure that force. We could observe the acceleration of the little test charge. So here's a test charge. It has electric charge q. It's an electric charge. You put it at some point x, you give it a little velocity, and you observe its acceleration. Well, from that you can determine it's the force acting on it. And the force is qv cross b. So measuring the force F is equivalent to measuring the magnetic field B. So that defines the field at any point in the volume. At the point where you put this little test charge, you can determine its force, its field at that point. It's basically the force divided by the charge divided by the speed. But there's a complicated direction involved because of the cross product. But that's taken as the definition of B of x. It's the force per unit charge, per unit speed, acting on a test particle. Now the directionality is complicated because of the cross product. Maybe you've encountered cross products before when you studied algebra or geometry. It's a topic in vector algebra. So let's have a quick review of the cross product. If you're not familiar with the cross product, you have to read very carefully in the textbook. There'll be a review of the cross product in the textbook. Or you can look it up on Google. You know, you could do a Google search. You could say, describe cross product of vectors. Here's a picture of a cross product. Well, first of all, understand, given two vectors, say A and B, the cross product is a third vector. Call it C. So we write C is equal to A cross B. And here's a geometrical picture. We have two vectors. There's A and there's B. And they cross each other. They're not parallel. They cross over each other. So here's A and B. They're in different directions. Let's say the angle between A and B is theta, not equal to 0. C is this vector. It's perpendicular to A. It's perpendicular to B. It's in sort of the third direction. A and B defines a plane. Two vectors define a plane. B is perpendicular to that plane. So this vector is perpendicular, and this vector is perpendicular. This vector is not perpendicular. Theta is not perpendicular. A and B can have any angle. Well, 0 is special, but any non-zero angle. C will then be perpendicular to the plane spanned by A and B. Well, that tells you the direction. Oh, that tells you two possible directions. Is it perpendicular upwards or is it perpendicular downwards? Well, it's the direction given by the right-hand rule. If the fingers of your right hand curl from A to B, then the direction will be the direction of your thumb, upwards. So if these are the directions of your fingers, this is the direction of your thumb. And C is in the direction given by the right-hand rule. All right, so that's the direction. Now what about the magnitude? Well, geometrically, the magnitude is AB sine theta. When I write C with an arrow over it, I'm talking about the vector. When I write C without the arrow over it, no arrow, I'm talking about the length of C, the magnitude of C, the magnitude of the vector. So C is AB sine theta. If A and B were perpendicular, theta equals 90 degrees, then the sine of theta would be 1, and the length of C would just be the length of A times the length of B. But, you know, if A and B were at 45 degrees, then the length of C would be AB over the square root of 2. That's a geometrical picture of cross product. All right, now, we often have to calculate cross products, and we don't use the geometric picture. We normally, or usually, we use algebraic equations to calculate a cross product. Suppose we have a vector A, which has three components. AX is the component of the vector in the x direction. AY is the component of the vector in the y direction. And AZ is the component of the vector in the z direction. In 3 dimensions, a vector has 3 components. And similarly, B similar. Bx, by, bz. Now what's A cross B? Well, A cross B is C. C will be similar. It'll have three components: Cx, Cy, Cz. And those will be related to the components of A and B by these equations. So for example, C in the x direction is AYBZ minus AZBY. C in the y direction is AZBX minus AXBZ. CZ is AXBY minus AYBX. You see, it's a product of a component of A times a component of B minus another product of a component of A times a component of B. The two components are different coordinates, and that gives you the cross product in the third direction. You can sort of see here the order of the indices here. Here is XYZ, XYZ. Here is YZX, YZX. Here is ZXY, ZXY. So they're kind of cyclic permutations of X, Y, and Z. Now, to remember this, we have a little mnemonic. So here's a mnemonic for remembering the cross product of two vectors. It's a kind of determinant. You can think of it as the determinant of a 3 by 3 matrix, I, J, K. Those are the unit vectors in the X, Y, and Z direction. AX, AY, AZ, that's the second row of the determinant. BX, BY, BZ, that's the third row of the determinant. If you think back to high school algebra, you remember, how do you calculate a determinant? Well, for example, one term would be I hat AYBZ minus AZBY. Well, that's I hat CX. And then J hat AZBX minus AXBZ. Well, that's J hat times CY. And K hat AXBY minus AYBX. So that's K hat CZ. So we're not going to use matrix mathematics in this course, but this is what you call a mnemonic. It's just a way of remembering. Just remember, it's the determinant. That will tell you these three equations. Okay, so that's an algebraic method of calculating cross products. You probably have to use that on some ln kappa problems. Well, the third section of chapter 18 is about applications of the magnetic force. And most of these applications have to do with circular motion of a charged particle, electrically charged particle, in a uniform magnetic field. So here's a picture. We have a uniform magnetic field. Uniform means it's the same throughout this whole volume. It's just constant. At each point in the volume, there's a magnetic field vector, let's say pointing in the z direction. And in this magnetic field, there's a charged particle, Q, electrically charged. So there's a little electric charge here. And it has a velocity. Well, there's a force acting on it. There's a magnetic force in the direction of V cross B. Now use the right-hand rule. If the fingers of your right hand point in the direction of V and curl into the direction of B, then your thumb points in the direction of F. Well, it's perpendicular to V, it's perpendicular to B, it's pointing in the direction toward the center of this circle. So there's a sideways force on this charged particle. The magnetic force on a moving charge is directed sideways, perpendicular to the direction of motion. That has a consequence that the magnetic force does no work on a charged particle. The magnetic force does no work on a charged particle because the force times the displacement is zero. F dot ds is zero. Remember, the dot product is force times distance times the cosine of the angle. Well, the angle's 90 degrees. The cosine of 90 degrees is zero. So the displacement, which will be in the direction of v, is perpendicular to the force. So F dot ds, that's the amount of work done for that little displacement, is zero because the two vectors are perpendicular. So the magnetic force does no work. And you remember from mechanics, the work done is the change in kinetic energy, or the change in speed, related to the change in speed. Well, there's no work done. So the speed of the particle is constant. Of course, the velocity is not constant. The velocity is changing in the direction of the force, qv cross b. But the speed is constant. And so the result is circular motion. This is an example of uniform circular motion. A charged particle moving in a uniform magnetic field undergoes uniform circular motion. It has a centripetal force, which produces the centripetal acceleration. The force is the magnetic force. It's perpendicular to the velocity, so it's towards the center of the circle. As the particle moves around the circle, at every point there's a point towards the center of the circle. The force is constantly changing in direction. It's always towards the center of the circle. Well, that's called uniform circular motion, with a centripetal force producing a centripetal acceleration. And the force is qv cross b. So there'll be a bunch of long capital problems where you have to consider circular motion in a uniform magnetic field. Circular motion of a particle in a uniform magnetic field. Now, there's a lot more to say about the magnetic force. For example, how the magnetic force is used in an electric motor. An electric motor has a current loop experiencing a torque due to a magnetic field. And that causes the current loop to spin. So an electric motor has a rotary spinning coil. That's the rotation which makes it possible for the motor to do work. But anyway, I'll leave the screencast topic at this point, and you can read about examples like motors in the textbook. Now, there is part 2 of the screencast. Part 2 of the screencast describes something different. It's the answer to this question, or it'll be some examples answering this question. Given an electric current, what's the magnetic field created by that current? We've been talking about the magnetic force. So there we're given a magnetic field. What's the force? Okay, but what created that magnetic field? Well, the answer is an electric current. Well, how does that work? Given an electric current, what's the magnetic field created by the current? So that'll be the subject of part 2 of the screencast.